I want to start kind of by going over where we're headed for this particular section. It is considerably shorter than the last one we did for test 1. But where test 1 was supposed to be a review of material that you already knew when you walked in here, then test 2 is not necessarily something that you've had before. And many of you have, but then still, when we're dealing with something like radicals, and that's what we're dealing with in test 2, we decided to just group it as just those 3 little sections. It's more sections, but 3 days worth of work, and then test on it because it sort of separated it, and you would be able to concentrate on just one subject or one area of this mathematics of algebra at a time, okay? So for this particular one, we're just going to have 3 days that we cover it, and then we go straight into test 2, which will be, when is our test? It is the 4th, okay? So this test is going to come up a lot quicker than the last one, is what I'm trying to say. It's really important because the tests are going to start coming quicker that you keep up with your work in My Lab Math. Let me tell you that I noticed another thing when I was grading tests. Another thing that's going to be really important to you is that you do not use help me solve this too much. Because I know some of the homework I'm seeing hundreds, and then I look back and I say, how much time did they spend on that? And it wasn't a whole lot of time, and I think, okay, well, they're getting it. You know, this student has not spent a lot of time on the homework, and they're making hundreds or 90s. And then I got to the test and didn't do so well. And the only explanation I have for that is that homework was not really a true score, was it? That homework did not represent what you actually knew. It was actually what you had helped me solve this do, or an app on your phone do, or a friend help you with. And that's just what I see a lot in this class, okay? So when that happens, guys, you don't actually learn the material, and when you come to the test, you can't do so well. You know what I'm saying? So the homework is there for a reason. It is not a torture process. It is a practice for you to see what you know. Homework grades may seem like they're just vitally important to you, but if you look at the absolute, how much do things count in this class toward your final grade, your tests count a lot more than your homework. And the reason that we put homework out there as a low stakes type of grade, and that's what that is a low stakes, is so that you can practice and get the practice you need, okay? It's not going to make or break your grade. Your homework scores won't do it, but your test grades will. Do you understand what I'm telling you? Take help me solve this and use it, but if it's not helping you learn the material, it's not helping you. And that will show up on your test scores, okay? So, bottom line is you're just going to have to, you have to dig in with math. This is not something that I know a lot of you want to hear, but it's going to take a lot more time. You have to dig in and you have to learn it, and there's no other way. There's no other way through this class, and you absolutely can't get around it if you want to go to college algebra. Okay? All right, so I'll talk to you individually about your test grades as we go. But for right now, let's start on a new subject, all right, or a new area of algebra. And this is called radicals. And radicals are what you might call roots, all right? We start out with square roots, and the square root is the one you're very familiar with. It has this little radical sign, and instead of an index over here where n is, it doesn't have anything. If it doesn't have any number there, we understand that to be the number 2. In other words, it's a perfect square. We were looking for squares of a certain number. We're looking for squares of whatever is under the radical sign, and that's called the radicand, okay? So we're going to be practicing today. We're going to be practicing finding the perfect squares that are under that radicand, or the perfect cubes, or even the perfect fifths that are under there. It doesn't matter. You can easily find any of them. I'm going to show you a procedure that works for everything, okay? I'm not going to go over 2 procedures because you guys taught me really quickly when we were doing synthetic division that you preferred synthetic division. You don't want the long, complicated way. So what I'm going to do is go over the easy method of doing this that will work for every problem, all right? Learn this method and you'll be fine with it. Now, there's some details here that I would suggest you look back at later. But if I go over them right now, it's just going to kind of confuse the issue. We need to kind of do some examples first. I also want you to notice down here we have two methods for solving under the radical. And the one that I'm really going to use is going to be method 2. What we're going to do is we're going to write the prime factorizations of these things. We're going to group them to find perfect whatever we're looking for, and then we're going to simplify it. And that method to me is a little easier, all right? So let's take an example down here. You got your paper. Everybody got a calculator out too because you're going to need it today. Simple calculator is going to be your friend when you're doing these things, and I'll show you why. The first step in simplifying under the radical is break it down to primes, okay? And primes, of course, prime factors are factors that cannot be multiplied by anything except themselves and the number 1. In other words, there are no factors of a prime number except for itself and the number 1. It doesn't divide any further. So if I look at 175, I'm going to come over here and I'm going to say I need perfect squares that are inside the number 175. The first thing I note is that 175 by itself is not a perfect square. There's nothing multiplied times itself that will give me 175, okay? So I got to go and break it down. And the way I break it down is I look for the smallest number that will evenly divide into 175. And if it ends in a 5, divide it by 5, okay? And you break it down like this with a little tree format. And you say, okay, 5 divides into 175, and here's where I'm telling you, take your calculator and say 175, and then say divided by 5. Okay, and it gives you a number, 35. That is the other factor. 5 times 35 gives me 175. Okay, I finished. 5 won't break down any further, but 35 certainly will. I take 35 and I say, well, it ends in a 5 too, so I know it'll divide by 5. It really doesn't matter what number you start with. You'll end up with the same factorization if you go down, you just keep going. Well, this one is 5 times 7. Well, now I'm done because 5 is prime, this 5 is prime, and that 7 is prime, and you see them at the end. That's the prime factorization of 175. What I'm trying to say is 5 times 7 would give me 175. You understand that, right? Everybody good with that? So I could write this under the radical sign as 5 times 7. I've broken it down into primes. I've written just the prime factors under the radical, and now I'm looking for pairs that are the same. Why am I looking for pairs? Because this index here is a 2. I want pairs of 2, okay? This one, these two, 5 times 5, there's my only pair I see. I can bring it out from under the radical now as just a single 5. Because that really is 25, isn't it? And the square root of 25 is 5. I can take it out from under the radical. You see what we're doing? What can I not take out from under the radical? That's 7. And I always circle those so I don't lose anything. So now, 5 times 5, I will break it down, take the square root. It's going to come out from under the radical. When it comes out from under that radical sign, it goes in front of it and is multiplied times whatever is left inside. How do we simplify the square root of 175? It's 5 times the square root of 7. That's all we can do with it. Did that make sense? Say that again now.
If we can square root anything that can go outside, the prime number stays in the radical?
Yeah, the prime number stays under the radical. If you can't take a square root, this one is squares, all right? If you can't take the square root of it, it can't come out. We're not going to decimals. I mean, I know your calculator will do it and give you a really long, that's not what we're doing. We are simplifying radicals and leaving under the radicand. We're leaving, under the radical sign, the radicand is now whatever was unable to be factored out. Does that make sense? We'll do another one. All right, now I've got 18. I'm still dealing, notice your index, I'm still dealing with squares. But the other thing you've got to notice is there's a coefficient out here. There's a 3 that's already been brought out from under the radical somehow. It's 3 times and we can't lose that. But we're going to come over here and we're going to factor this 18. Now, if I have an even number, I start with the number 2. I got to break it down all the way down. So I'm going to say 18 divided by 2. I don't need a calculator. That's 9. 9, well, that won't divide by 2, but it will divide by 3. And now I've got my prime factorization of 18. I do see that I have 2 3's, so I'm going to rewrite this. I'm going to say 3 times under the radical. I have 2 3's, and I kind of like to write the pairs first. You don't have to, but it's nice to write them together so that you can see that I have a pair that can come out from under the radical. I can take the square root of 3 times 3, and it's just 1 3, isn't it? What's left? I can't take the square root of 2, so it's stuck under the radical. Now, this 3 that came out would go in front, but there's already a 3 there, so I multiply it times whatever's in front. In other words, I say 3 times 3 times whatever's left under the radical, 2. Can you simplify that further? Yeah, you could say 3 times 3. That'll give you 9 times the square root of 2. Are you okay so far? This is all we're covering today, but we're covering some complicated problems. They get a little more complicated than this. Let's go to the next page. Now this time I've got 121 x to the power of 7. Anybody see anything special about 121 right off the bat? It's a what? Yeah, it's a perfect square, right? It's a perfect square. I mean, it already is a perfect square. So to factor 121, I can come over here and try everything in the world, but the only thing it's going to factor into is 11 times 11. It's nice to know your perfect squares up to 13, okay? If you don't know them, then memorize them. Go look at them. 1 times 1 is 1, 2 times 2 is 4, all the way up to 13, guys, okay? It's not much memory that you need to know, but you do need to know that so that you can recognize some of these numbers. All right, so I got 121. I'm going to write it again. I'm going to say 11 times 11, and then I've got x to the power of 7. Now, here's the deal if you have an exponent, okay, a variable with an exponent. You want that exponent to be evenly divisible by the index. Well, the index here is 2. 7 is not evenly divisible by 2, is it? Okay, so what's the biggest number under 7 that is evenly divisible by 2? 6. So let's factor it into x to the power of 6 times what's left over? X. And you can write to the power of 1 if you want to remember that, okay? When I multiply the same base with exponents, I add them. Some of you missed that on the test. When I multiply the same base with exponents, I'm adding exponents. So that's how, do you understand that breakdown? So far, are you good? All right, now let's get the perfect squares out from under the radical. 11 times 11, well, that's a pair. When I bring it out, it'll be just plain 11. X to the power of 6, if the index is if the exponent is evenly divisible by the index, that's what you do. You say x to the power of 6 divided by the index of 2. Well, what's 6 divided by 2? So this is x to the power of 3 when I bring it out. 6 divided by 2. It's simple. Exponents are easy. What's left that I cannot bring out from under the radical is x, or x to the power of 1, okay? So how do I write this? Well, these things that I brought out have to be multiplied times each other, and they become the coefficients of this, whatever is under that radical sign. What's left is only x. So that's simplified. Square root of 121x to the power of 7 is really 11 times x cubed times the square root of x. And look under your radical. It can't go down any further. There's no way I can take the square root of x, is there? All right, next one. I'm going to do this one. I really don't want to do it as a cube. I want to do this one as a perfect square, okay? First one I want to do is a perfect square. So we're going to do 250, we're going to do the square root of 250, okay? Now that's, I'm not sure what perfect squares are inside 250. I kind of am, but I'm going to break it down like I don't know. If I don't know and it's an even number, you divide the thing by 2. And then you say 250 divided by 2. Well, that is 125, isn't it? It's easy. It gets easier as you go. Well, 125 will not divide by 2. It's not an even number. Let's try, but we know it isn't a 5, so it'll divide by 5, won't it? 5 times what is going to give me 125? Does anybody know? 25. Okay, 25 will break down into what? What are you going to divide it by? 5. And that just happens to be a perfect square, 5 times 5. So now here are my numbers, 2 times 5 times 5 times 5. Can't go any further. I have got the prime factorization of 125. I will write it under my radical. Remember, we changed it to a square root. And I'm going to write the multiples first, just because it's easier when I'm trying to get them out from under. That's really the square root of 250. It's really the same as the square root of 5 times 5 times 5 times 2. Now, I can bring out pairs, can't I? I have one pair here, 5 times 5. When I bring it out from under the radical, it is a 5. But now I only have one 5 left. I can't do anything with that. And I have a 2 that's all by itself, so those are stuck. So I end up with 5 times the square root of 5 times 5. I'm sorry, 5 times 2, which is really 5 times the square root of 10, right? How's that? Is it getting simpler? We're doing the same thing over and over again, so it should be. Any questions? Anything that's not clear on the process we're doing? We haven't gotten, the next thing we're going to hit is the cube, okay? We've been working with the index of 2, square roots. Now let's see what happens when we change the index. This next problem, and that's why I wanted to change that 250, square root of cube root of 250, it was a misprint. This one is the cube root of 250. You start off the same way. Break it to primes. 250 to primes. Well, I already did that, right? It's 2 times 5 and 25, right? And this 125, not doing this right. And this is 5 times 25. And this would be 5 times 5. Could have just gone ahead and written down what I know it is. So this is the cube root. And I'll write them again. All the multiples I'll write first. Prime factorization doesn't change just because the index changed on your radicand, does it? A radical. Okay? So now what are we looking for? Before we were looking for pairs of numbers. Now we're looking for sets of 3. Because the index here is a cube. So we're looking for multiples of 3. All right, I have 1. When I bring out the cube root of 5 times 5 times 5 is 5. Right? Doesn't that make sense? Cube root would just be one of those one of those 3 numbers multiplied times itself. All right, what's left that I can't do anything about is this 2. Okay, so the 5 goes out as a coefficient. I have to remember that that 3 is really the index. It's not the coefficient. And what's left under the radical? 2. So this is 5 times the cube root of 2. How's that? Now you can find any factorization. You break everything down to prime. You look at the index and you say, I want multiples of that number. I want sets of 3. I want sets of 2. I want sets of 4. Bring them out from under the radical that way. Your exponents for variables works exactly the same way. I think I've got a chance to show you that right now. This one is 128. We start off the same way. We're going to break it down. We're going to break it down by factoring, prime factorization. It's an even number. Divide it by 2. It's another even number. Divide it by 2. It's another even number. Divide it by 2. Anybody can do this type of math, guys. It's another even number. Divide it by 2. I don't need the calculator at this point. I keep dividing by 2, and look what 128 factors into. A bunch of 2's, doesn't it? It goes all the way down, just 2 times 2 times 2. How many times? How many 2's do I have there? Somebody count them. 7. So I'm going to rewrite it. This is the cube root of 2 times 2 times 2 times 2 times 2 times 2 times 2, and check and make sure you got 7. And then I've got x to the power of 8. I need multiples of what number? That exponent needs to be multiples of what? Not 2 this time, 3. Well, 8 will not evenly divide by 3. What's the next biggest number inside 8 that would evenly divide by 3? 6. Let's factor this into x to the power of 6. That'll divide by 3. What's left when I did that? That's it. Make sure you understand that, because like I said, that was highly missed on this last test. We did have one perfect score in this class. Yay. Okay? Now look, does that make sense? X to the 6 times x squared, add exponents. When I multiply the same base with an exponent, I add them. So that gives me my x to the 8th. 2 times 2 times 2 times 2 times 2 times 2 times 2, well, that's my prime factorization of 128. Now, I'm looking for sets of 3. Well, here's one set of 3. When I bring it out, I have just 2. I got another set of 3, don't I? When I bring it out, I'll have just 2. And this one is, I'm stuck with that one. I always circle it, because if I don't circle it, I miss it. Chances are, if I have to do that, then you probably have to do that too, okay? Don't just say, I'm going to remember that I don't have to circle or whatever, because that's where I always find I make mistakes. Now this one is divisible by 3. When I divide 6 by 3, I get 2. Remember, you're doing division on that, all right? I'm saying the perfect cube in x to the power of 6 is x to the power of 6 divided by the cube, right? 3, and I get 2. This one I'm stuck with. Okay? All right. So let's do what's out front. Everything here has to be multiplied together. 2 times 2 times x. Do I need to write that down, or can you guys tell me what that is?
4x squared.
Yes, thank you. It was x squared, wasn't it? That's 4x squared. And now we're to the radical. It's a cube. Don't forget your index. What's left under that radical sign? That's right, 2x squared. This is really not hard. Is it? It's not hard. Algebra's not hard. It's just learn the process. You know, if you go through the same steps every time, you will get the right answer. Okay, you good with that? All right, let's do another one. The cube root of 16x to the 18, y to the 4th. Well, primes of 16. It'll divide by 2. It'll divide by 2. It'll divide by 2. And I ended up with all 2's. Did you guys end up with all 2's? So I'm going to say this is the cube root of 2 times 2 times 2 times 2. Well, I took care of the 16 now. Let's break these down into multiples. Let's break these indexes down, these exponents down into multiples of 3. Is 18 divisible by 3? Okay, well then we can leave it. Is 4 divisible by 3? So we got to factor it. What is it? What are you going to factor it into? Y to the something. That's it. If you need to write a 1 for that index to understand what's happening there, go ahead. You see it? Adding indexes, adding exponents, I get to this, that's how I got back to the y to the fourth, okay? All right, now find me perfect cubes under here. Sets of 3, right? There's one. When I bring it out, it's just one of them. This one, is it divisible by 3? Yeah. When I divide it by 3, the exponent, I get 18 divided by 3 is 6. What about this one? When I divide that by 3, I get y. Whoops, forgot to circle this leftover 2. And I can't do anything with this one either. So the coefficient of this thing, what's left out front? I multiply everything I brought out together. 2x to the power of 6y times the cube root of whatever's left over, 2y. Right? Okay, not so hard, just takes practice. Now let's look at this next example, 8. It's division. And while that looks like, and this is, I can't tell you in division of radicals that you always do the same thing first, because it depends on the problem. This one has a radical in the numerator and a radical in the denominator. And I look at it and I go, well, okay, I can't get the square root of 21 and I can't get the square root of 3. Maybe I'm stuck with it. Maybe that's the simplest form. But here's the problem. Are you listening to me? You can't leave a radical in the denominator of a fraction. I got to get rid of that square root of 3. Well, how do you do it? There's several ways that we will work on, but the first step is this. Look and see if they would simplify if they were all under the same radical sign. In other words, 21 divided by 3, does that give me a whole number? Mm-hmm. Yeah. So what is this? It's the square root of 7. I can't do anything with square root of 7. That must be its simplest form. I no longer have a radical in the denominator. That was the goal, right? So that's the simple version. Okay, I want to look at another one. I want to go straight down here. I want to do number 10 next, okay? So, same thing. Can't get the square root of xy. Got to get the radical out of the denominator. I'm going to try putting it all as one fraction under one radical sign and see if I can simplify it down to a whole number, no fraction, right? See if I can get rid of the fraction. Well, these will reduce, won't they? Some of this was on the test, and you've got to remember, when I'm dividing, I subtract the exponents. I end up here with x to the 6th in the numerator. I subtracted 7 minus 1, and where did I put it? Numerator, because that's where the bigger exponent was. I say 5 minus 1, that's y to the 4th. Numerator again, right? True? And this is the square root. It didn't come out from under the radical, but it is no longer a fraction, is it? The best thing to do is get rid of the fraction if you can. Put it all under one radical sign if it's under 2, and see if you can get rid of the fraction. See if you can simplify. Am I done with this one? What do you see? No. Okay. Yeah, the exponents can be divided by 2. We can take the square roots, can't we? I can take the square root of x to the 6th, I divide it by 2, and I get x to the power of 3. I can take the square root of y to the 4th, I divide that exponent by 2, and I get y squared. So what is this? X cubed, y squared. Nothing is left under the radical, is it? Do you see it? Okay. All right, let's go straight down. This time, it was all under one radical sign. But I can't simplify those together and get rid of the fraction, can I? This is why I told you there's no there's no one starting place for these problems. You just got to look at it and say, what can I do? What can I do? If it doesn't simplify under the radical sign, then what can I do? Well, I can split it up into two radicals. I can split it, and then I can try and see what's next, okay? Try and see what's next here. Well, this is a perfect square, and that's a perfect square, isn't it? Thank you. I knew I'd done something wrong. Now, this is a perfect square, and that's not, but we can take care of this. This is x squared times y squared times y. Now, this one will come out. It becomes just x. This one will come out. It becomes just y, and I'm stuck under the radical with that one. That's the numerator. What do you know about 100? It's a perfect square. Isn't it 10 times 10? Square root of that is 10. You didn't have to go through that step if you saw it, right? You just say, okay, the square root of 100 is 10. Now, how do I write this? Well, these came out front, x, y, and under the radical I was stuck with that y. That was my numerator. My denominator was just a 10, and that's it. I'm left with a radical in the numerator, and that's okay. What's not okay is a radical in the denominator. All right? Any questions on those? Because I've got two I want you to try back here on your own. This one is a bit of a challenge. It's a perfect fifth, okay? The root is a 5. Give it a try. You're looking for multiples that are the same number multiplied 5 times. You're looking for this index or this exponent to be divisible by 5, okay? Try it. And then try this one down here, which is not going to be so difficult. Okay. Yeah. Okay, good job, because most of you have brought up some things that I wouldn't have thought to mention if you hadn't come into these problems, so I want to go over them with you so that everybody can benefit. This is a factorization of fifths. We're trying to do perfect fifths. We have to have the same number multiplied 5 times. When we come over here and we break 50 into primes, we're going to end up with no numbers that are multiplied 5 times. Most of you figured that out. What I didn't think to mention to you, or maybe didn't make clear, is this. Guys, it doesn't matter what number you start dividing by. If you keep going, you will finally break it all down into primes. In other words, I could say, well, that's divisible by 10, couldn't I? Okay, that one's prime. And then I can break 10 down again. Well, I can divide it by 5. You just keep going. If you see a number that it divides by, doesn't matter where you start, you will end up with the same factorization at the end. 5 times 2 times 5 is the same as 2 times 5 times 5, or 5 times 5 times 2. It doesn't matter, right? So when you keep going, you just divide by something. And if that number will divide again, you divide that number by something. It's just easy if you get a pattern going in your head. If you say, okay, every time I see an even number, I'm going to divide by 2. Every time I see something that ends in a 5, I'm going to divide by 5. And then that helps you just to have a system that you always go through, okay? But you will end up with the same numbers. This ended up being the 5th root of, and I'm going to write the multiples first, but there aren't enough of them. I don't have enough matching numbers. So I know, even before I get over to this variable, I know I'm stuck with all 3 of those. You see? They can't come out from under the radical. I don't have 5 matching factors. Now, I can break x to the 22nd down into groups of 5, right? Groups of 5. Well, how would I do it? What's the biggest number under 22 that is evenly divisible by 5? Right? How many groups of 5 would you get in 20? 4. And that's what you're looking for. So then I was got to say, what's left over? Okay, so that one will not come out from under the radical, but this will simplify. I say 20 divided by 5. In other words, what I'm saying is, how many groups of 5 do I have in 20? Well, there's 4 of them, right? This is really x to the 4th times the 5th root of 50 x squared. How did you do on that? If you got part of that, I'm happy at this point, okay? If you got part of it, I'm really happy. Okay? Okay. Now, yeah.
So why did the 5 should go to the outside? Did you get that with the second question?
Over here or over here?
Yeah, right there.
This one outside?
No, the 5 times 5.
It doesn't matter. When under there, what order you write them in doesn't matter. I simply write the multiples first. Okay? It helps me, because then I'll say, okay, how many do I have? How many 5s do I have? I need 5 things that are matching. I don't have 5 matching numbers. Okay? I could have written 5 times 2 times 5, but that wouldn't have helped me find sets of 5. okay? All right, let's look at this next one now. This is pretty simple. When it comes down to exponents, I'm looking for multiples of 3, right? Well, this one is a multiple of 3. I know I'm going to be able to bring that one out as an x. This one is a multiple of 3. I know I'm going to be able to bring that one out as y cubed. This one is not, but the biggest multiple of 3 under 7 is what? So I'm going to write it again, x to the power of 6 times, z, right, to the power of 1. This one will come out as z. 6 divided by, I have to say this in my head every time I do it. So I pretty much think you probably should too. I'm going to say z to the 6 divided by 3 is 2. Okay? Just so I know what I'm doing. And then I've stuck with this one. And this q to the power of 5, I need sets of 3. What's the biggest set of 3 under there?
3.
Yeah, so I got q cubed, q to the power of 3, times q to the power of what? Isn't that what's left over, right? Cubed times squared. I would add them together this time and get, that's how I got back there. And this one simplifies, doesn't it? To just plain old q. I'm stuck with that one. Are you good? This became, what's out front? Well, all of these are out front. This is x, y cubed, z squared, q. That q looks like a 9 quite often. Be careful when you're writing q's, okay? You might put tails on them so that you don't get them confused. And then we have an index, a radical. It's a cube root. What's left under there? Well, I circled them so I didn't lose anything. Z q squared. I'm going to tell you this because I'm going to say this a lot as we go further into algebra. You don't have to look at the problem and know what the solution is. A lot of you get lost in the fact that you look at a problem and you say, I don't know how to solve that. Do you know how to do the first step? Okay? Do the first step. And then look at it again and say, okay, now I see a second step. I see something else I can do. You have to work algebra like that. It's in layers, okay? You can't just look at it and say, I'm going to know how to do this problem when I glance at it. That's considered to be level of expert. And I don't think any of us are there yet. So, all right? You'll get there. I know I do have your test. Let me cut off the recording because I don't want this on the recording.